Given a string S and a dictionary of strings, word dict, check if S can be segmented into a space-separated sequence of one or more dictionary words. If yes, return true, else return false. The same word in a dictionary may be used multiple times. Constraints, example. So cats and dog. Is there a way we can add spaces and separate this in such a way that all the words we see will be present in the word dictionary, like the word dict? And the answer is true. Cats and cats with an S. Notice it's different from cat. Cats and dog. Because in this case, there's no way, right? Because cats is pluralized. And dog doesn't have a G, it's missing a G. So there's no way we can break this with spaces so that everything fits neatly in here. Because if we add a space, there's no OG in here. If we don't add a that's the only place it seems reasonable to add a space anyway. And there's no OG in here. So what does the solution to this look like? Essentially, we're going to do what we've been doing from the get-go. We have this string, then we're going to create a lookup table and add one to it that represents an empty string, because an empty string is can be considered part of a solution, right? The empty string at the beginning of the word. And we have this arrangement. So we initialize that to true, right? Everything here is either going to be true or false, meaning we can find it there. And then because this is true, this says, oh, there is an empty string in there. It's possible to construct an empty string, which we will assume is part of the dictionary in here. And we set it as true. And that's important because we're going to iterate over the input string with I. I is going to loop through this entire string. And J is going to loop up until I. And when we do that, we're going to see how it's going to work. So let's look at some code, right? We have this word break function. We have our string. We have the word dictionary. We set n to s the length of the string. Then we get our set so that we can look it up in constant time. We can look things up in constant time. And then we initialize lookup table, n+1, fill everything with false. Set the first element to true, represents the empty string. Then begin the looping. So we loop from I to n all the way up to n. And for j from 0 to less than I. And what are we checking? Okay, so we have these 2 pointers and we're gonna loop through everything here. Pay close attention. So the first word, right? The first thing that happens at j, v is not in a dictionary, right? And we check that. Does the word have the substring at j and I? It's not there. dpj is also false, right? So this indexed at, in this case it's true actually, because j is 0. So it's true. However, v is not in the dictionary. And so this doesn't trigger, right? So dp is not updated. And so we move on, right? We're searching for something. So we don't update this to true. Now we have VE, I moves on to VE. And as you can see here, I is going to move on, J is going to move on. J is broken, right? It's done its loop, it's reached I. So I is going to increment now, so it's bigger, the window is expanding. And VE is not in the dictionary. So despite the fact that D of J, right, is true in this case, it's not in the dictionary. This check returns false. And so this branch doesn't execute. And so we just keep moving. J then moves forward. E is not in there, so that it reaches the end to reach I. So I now expands and J resets again. Now we have VEG. Oh, how about that? In this case, D of J is true, and if we slice this as we do here, the substring, if we slice this, it is actually in the dictionary. How about that? It's actually in the dictionary. And so because D of J is true, so because this whole thing and everything before it, the empty string, which is here, is true, those 2 conditions need to be true, then we can update this to true. Okay, so we found something, we can break out of it. We don't need to we don't need to check further smaller substrings, basically. So because of that, you notice in this case, J didn't continue iterating up to I, right? We just moved I instead, because and that's what the break does here. It breaks out of this inner loop for J. And then we check Vega. Vega doesn't exist, same story. But in this case, J keeps moving, right? Keep checking smaller things. A doesn't exist. Now it's reached I, so I is going to expand. And then we're going to consider vegan. Now vegan isn't there, so the same story. We now start moving A forward, and now we have A and N. So now we check, okay, D of J represents VEG. That's what that represents, right? Up until G. And it's true. We can find VEG in the dictionary. So there's a way to add a space here and begin A and N, right? And that would appear in the dictionary, assuming we stopped here, assuming we're considering the string only up until here. So that would be true as well. However, we still have more work to do. So we then, and because we found it, right, we don't have to move J again one more step, right? We break out of it and move I instead. So the final point, which is N. So basically now I is equal to N. And we check vegan D. Oh, that does not exist. Then we keep moving J up until I, and we stop here. We see and. So in reality, with the real string, VEG exists, right? That's why D of J is true. And we're using the sub problems to compute find the final answer. And that final answer here, right? Because I is what it is. We then update I, dp at I to true and break. So we're done looping through this. And at the end of the day, we return the last thing that we found, which is this. And then that lets us know that, yep, there's a way to separate this with spaces so that when you add a space, everything, all the individual words it was broken into can be found inside of this dictionary. So next, let's look at the time complexity of this problem. It's n squared. Again, a loop inside a loop up until I, so we can approximate it to n squared. And then the space is O of n, because the lookup table, right, that we created is directly proportional, grows with the size of the string. And that's all there is to this problem. Thank you.